So this is section 3.1. We're going to talk about some further identities for our trig functions, pretty much based on our fundamental identity for sine and cosine. And also, we'll talk about the oddness and evenness of the various trig functions. Well, we kind of touched on that in the last section with tangent, but we'll talk about all the trig functions. Okay, so we'll start with identities. And the idea is we have our fundamental identity, sine squared x plus cosine squared x is equal to 1, right? We explained that, and we used it in some applications. But sometimes we do have to work with tangents, right? And other trig functions, secant, cosecant, cotangent, right? And the question is, we know that all of these guys are very related to each other, right? Tangent is sine over cosine, right? Secant is 1 over cosine, and so on. So if we have this fundamental identity up here, does that tell me anything about these other trig functions, right? Can I kind of create new identities that relate not just sine and cosine, but that relate tangent and secant or any of the other ones? Okay, and the answer happens to be yes. And it's actually very easy to pop out identities. So let's start with tangent. So let's kind of take this point of view. I want to figure out some sort of identity having to do with tangent and other trig functions. So I want to relate tangent with the other trig functions. All right. So I'm going to start with the fundamental identity, this guy here, which I know to be true. And I want an identity having to do with tangent, right? So I need to kind of modify this fundamental identity down here so that I can see a tangent. So tangent is sine over cosine. So what I'm going to do is I'm going to divide by cosine on both sides of this equation. And so what I end up with is that this is actually the same as sine squared x over, I'm going to divide by cosine squared x plus cosine squared x over cosine squared x equals 1 over cosine squared x. All right, so I divided through by cosine squared x. And the reason is because now this first term here, right, this is sine squared over cosine squared, right, which is tangent squared. And so that pops out the tangent for me, and that's what I wanted, right? I wanted an identity having to do with tangent. All right, the great news is this next term right here is actually just 1, cosine squared over cosine squared. And then on the other side, what is 1 over cosine squared? Well, 1 over cosine is secant. So the square of that is secant squared. So this is 1 over secant squared. Oops, sorry, is equal to secant squared. Sorry, 1 over cosine is secant. So 1 over cosine squared is secant squared. So we just get secant squared. All right, so that's it. That's our identity. It relates tangent and secant. Okay, and we can use this identity in much the same ways that we use the fundamental identity, sine squared plus cosine squared is equal to 1. For that one, for example, we said if you knew cosine of x was equal to 1/3, and you knew x was in the first quadrant, then that could tell you sine of x. So you can do much the same things here. If you know something about tangent of x, then you can figure out what secant of x is, right? And actually, if you know what secant of x is, you know what cosine of x is, because cosine of x is just 1 over the secant, right? And so you have this interrelated identities that tell you, essentially, if you know one of the trig functions, then you know all of the other trig functions, right? If you know cosine of x is equal to 1/5, right, and x is equal in, let's say, the first quadrant, then you know sine of x, you know cosine of x, you know tangent of x, and so on. All right. Okay, so that's one identity. Very straightforward. Now, of course, we have other ones. Let's see. We have an identity relating sine and cosine. We now have one relating tangent and secant. right? What about cosecant and cotangent? Well, those are just as easy to get because cosecant of x, we said, was just the same as 1 over sine of x. Cotangent of x was 1 over tangent of x. But that's actually just, if you simplify this, this is 1 over sine of x over cosine of x. And that's equal to cosine of x over sine of x. All right? So actually, you can get an identity relating these two in the same way that we got the identity for tangent and secant. And you should do this. You find identity. Right? This is a really good exercise for you to see whether you understand the one we just did and whether you can kind of work more abstractly, which we're going to start to do more and more in this class. So up to now, it's been a lot of kind of compute this, compute that. What is sine of whatever, pi over 7 or whatever, right? Well, that one you don't know, sine of pi over 3, right? But now we're going to work more abstractly because we really need to understand these functions as functions, not just kind of individual values of these functions. So make sure you do this. You should definitely do this. Find the identity starting from the fundamental identity, sine squared plus cosine squared equals 1. Okay, so that's it. That's the first part of this section. So this is actually not going to be too long a section. The second part of this section is odd, even, etc. Or let me just write the last one, neither. Right? So this next one is the oddness or evenness of the trig functions. Actually, I should say something. Our book, so I'm just going to use odd and even when we talk about functions. You can also, an odd function, you can also say its graph has symmetry about the origin. For an even function, you can say its graph has symmetry about the y-axis. But we're not going to use that much in our class. You'll see that if you do take pre-calculus, you'll see that concept, kind of the concept of the symmetries of a graph. But we're not going to use that in our class. So I'm going to restrict myself to only talking about odd and even functions. So not the symmetry of graphs. Okay, so that the symmetry of graphs is actually a more general idea, but we don't need it because we're specifically working with functions. Okay. All right. So odd and even or neither. So we've already discussed in the last lecture that cosine of x was even. We said that sine of x was odd. We said that tangent of x, because it's equal to sine over cosine, this guy is odd, right? And we could do this for all of them. Secant of x is equal to 1 over cosine, right? And so that's going to be, secant is going to have the same evenness or oddness as cosine. So cosine is even, so this guy's going to be even, all right? Definitely make sure you understand that. And if you're not 100% sure, just confirm it by calculating, again, by just doing the definition of even or odd, right? Secant of x, compare it to, well, when we're asking whether it's even, we want to compare it to secant of negative x, and we want to know whether they're the same, right? Let me just do this one, and then I won't do any of the others. I'll let you do them. So this is this question mark here is the same as 1 over cosine. Is this equal to 1 over cosine of negative x, right? But we know cosine is even, so this is the same as asking is cosine x equal to 1 over cosine x? And the answer here is yes. So that's yes, so that's yes, and so secant is even. All right? Okay, so in the exact same way, cosecant, which is 1 over sine of x, is odd, right? We don't know the graph of secant or cosecant, but if we were to draw the graph, we know that secant has to have the evenness type of symmetry, and cosecant has to have the oddness type of symmetry. Okay, and then cotangent finally is equal to cosine over sine. and that one is even. That was, sorry, that one's odd again. All right, so make sure you're comfortable with those facts. But the important thing here is that our trig functions have this kind of symmetry, odd and even, odd or even. So make sure you also are comfortable with the fact, with how this translates to algebra, right? So for example, let me actually do it on the same page or the same lines here. Cosine x being even means cos x is equal to cos of negative x, right? Sine x being odd means that sine x is equal to, sorry, sine of negative x is equal to negative sine of x, right? Tangent being odd means tangent of negative x equals tangent x, but with a negative sign. Secant being even is the same as secant of x is equal to, I've been doing it that way, so secant of minus x, no, secant of x is equal to secant of negative x. And then cosecant being odd tells me cosecant of minus x is equal to minus cosecant of x. And then finally, cotangent being odd tells me cotangent of x, of negative x, equals negative cotangent of x. All right. And again, the one way you can always remember these, or one way you can think of these is, for sine, you have the minus x inside here can be pulled out to there. For cosine, the minus sign in here just is absorbed and it disappears. All right. It's kind of very dangerous to think of it that way, but you can think of it that way. I think a lot of people remember these properties in that way. All right. Okay. Now these together, this odd evenness of sine and cosine functions, together with the identities that we just talked about, those create a lot of the exercises in this section. So a lot of the exercises will be, you'll see, will be simplify. And then they'll give you an expression and you have to simplify it. All right. So for example, simplify sine to the fourth of, let's say, negative x minus sine squared of negative x over secant of x. All right. So they want you to kind of write this in a cleaner form. So what you want to do is use all the identities you know, all the features you know about sines and cosines and secants and tangents and so on, to make this guy look a little simpler. All right. So for example, I know that sine is even. Oh, sorry, is odd, right? So this sine to the fourth of negative x, this is the same. Let me do this in two steps just to avoid some confusion. This is sine of negative x, whole thing to the fourth, right? That's literally what that notation means. And this here is sine squared of negative x, whole thing, sorry, sine of negative x, whole thing squared, all right, over secant x. All right, so if you want to deal with this, that negative sign, now we can pull this negative sign like that, whole thing to the fourth, minus sine, sorry, minus sine of x squared over secant x. Okay, so I'm being very careful about my procedure here, right? So here in this step, let's see, to go from here to here, I've used sine is odd. And to go from here to here, I've just used the definition of, just a definition of the notation of sine to the fourth means that, sine squared means that. Okay. All right, luckily for us, these minus signs are just disappear because we have even powers. So this is sine to the fourth x minus, that one has a square power, power of 2. So this is just sine of x over secant of x. All right. Now we can actually, sorry, square there. We can actually simplify this more because actually I noticed there's a sine squared on the up here on the right, but there's also a sine squared on the left because sine to the fourth is sine squared times sine squared. So this is actually, let me write it in two steps, sine squared x times sine squared x. minus sine squared x, just so we can see it kind of more explicitly, right? Since we have 2 sine squared x's, we can pull it out. So this is sine squared x times sine squared x minus 1 over secant x. And why did I do that? Well, I know that sine squared x plus cos squared x equals 1, right? And so that means if I throw the 1 to the left and the cosine to the right, then sine squared x minus 1 is equal to minus cosine x squared x. Okay? And so this guy can be simplified to sine squared x times minus cosine squared x over secant x. And secant x is 1 over cosine, right? So this, I'm going to pull that minus sign out in front just to make it look a little nicer. Cosine squared x. Secant x is 1 over cosine, so this is 1 over cosine x. And so this actually, if I simplify this fraction, right, this kind of double quotient, I'm going to get sine squared x, cosine squared x, and then times another cos x. All right, so ultimately I get minus sine squared x cos cubed x. So this is a much cleaner expression than the one we started out with all the way up there. Okay, so that's the kind of stuff that you'll see a lot of homework problems on, and they're good problems because they kind of force you to think about all the identities, and they force you to think about which identities should I use here, which identities should I use there, and so on. Okay, let me do one more. But one thing to note here is, again, there's an infinite variety of these kinds of problems. So you just have to keep in mind all the different identities and just think, maybe I can use this identity here, maybe I can use that identity here. You have to kind of just take into consideration all the possibilities because every problem is different. There is no kind of algorithmic way to do these problems. All right, so let's say simplify sine. And you definitely want to get comfortable with this section because in the next section we'll be doing more with identities, and it'll be kind of slightly more involved computations. So make sure you're comfortable with these so that you'll be okay next week as well. All right, so let's simplify this guy. So again, we have our main identity, sine squared x plus cosine squared x is equal to 1, right? So essentially, anytime you see like a sine squared and a cosine squared, then maybe one thing you can consider is to convert everything into either just cosines or sines, right? So this fundamental identity allows me to convert sines into cosines or cosines into sines, right? By throwing one or the other to the other side. So whenever you do see sines and cosines together, or sine squares and cosine squares together, that's one consideration that you can think about. So here, I probably want to do that because my thought here is that I see cosine squared here, I see cosine squared here, so my suspicion is that maybe if I convert this sine squared into a cosine squared, then I'll have so many cosine squares that perhaps I'll get some cancellation, so everything will be nice and simple, right? So that's my kind of thought process. So what I'm going to do is I'm going to convert this sine squared into cosine squared, all right? And in order to do that, I use my fundamental identity. I see that sine squared plus cosine squared is 1, and so therefore sine squared is 1 minus cosine squared, right? So sine squared x is equal to 1 minus cosine squared x. And so every time I see a sine squared, I'm just going to replace it with cos squared. And so what I end up with is 1 minus cos squared x as that sine squared minus cos squared x over 2 cos squared x minus 1, right? So I converted this guy, sorry, the sine squared into that guy. Now, already I can see some simplifications. Cos squared is cos squared. So I get 1 minus 2 cos squared x over 2 cos squared minus 1, right? Okay, but look, these two guys are kind of, in a way, the opposites of each other, in that if I take the top term, for example, and I pull out a minus 1, then this is going to be minus 2 cos squared x minus 1, right? On top, and then just the same on the bottom. I didn't change the bottom. There should be an x up here. Okay, now the numerators are the same because this minus 1 distributes into here and into there, right? So I get minus 2 cos squared x, which is the same as above here, and then plus 1, which is the same as above here. So these two guys are the same. But the reason I did that is because now I can explicitly see that I have cancellation, and this is just minus 1. All right. So sometimes, things that look very ugly can have dramatic simplifications using our various identities. All right, so in the homework, certainly, so in these two examples, I've used the fundamental identity. But of course, now that I've given you the identities for tangent, right, all the way up here, right up here, right, I've given you the identity for tangent. That's a consideration, right? So if you do see in the homework tangent squared or a secant squared, perhaps you might, want to try converting the tangent squared into a secant squared, or the secant squared into a tangent squared, all right? And then, of course, you found the identity for cosecant, or the relationship between cosecant and cotangent. So if you see a cosecant squared, perhaps you want to convert it to a cotangent, okay? And again, also keep in mind that when you do see in these homework problems, if you do see something like tangent of minus x, you know that that's equal to, because tangent is odd, you can pull that minus 1 out like that, because tangent is odd. Okay? So things that may look complicated can become very simple with trig functions, because trig functions have a lot of nice relationships between each other, and because they have nice relationships actually within the trig function. And what I mean by that is even and odd, right? Okay, so next week we'll expand on this, and we'll talk about, actually, so I should probably say this now. Next week what we'll do is, right now we figured out an identity, right? For example, this identity again, all the way up here, the tangent squared x plus 1 is equal to secant squared x. Next week what we'll be doing is we'll be asking, I'm going to give you an equation, right? Maybe something that looks like this, and I'm going to ask you, is this an identity or not? In other words, is this equation actually true or not for every x? And sometimes the answer will be yes, sometimes the answer will be no, and you're going to have to try to figure it out. And how do you do that? You try to simplify the expression and see if you get something that is obviously true or obviously false, right? The same thing as what we did with even and odd in a way. All right. So you definitely want to be comfortable working the identities in this section so that you can do the same in the next section. But those ones are going to be more difficult because they're not as straightforward, because some of the equations will give you, right, they won't be identities. So you'll have to kind of discover that.